Good afternoon. Welcome to Lab 9. We are going to start by talking about the exam, which will be next Wednesday afternoon. Again, you'll be taking this online. The topics are going to be over the past 3 labs, well, including this one. So the first chunk of material, we were doing nonlinear systems of equations. And so we were using first Gauss-Seidel, which is that successive substitution technique. Remember that every time you calculate a new value, you're substituting that in. And that works often, okay? And at least it's easy. You don't have to do any advanced math or anything. And then the other technique we have is the Newton-Raphson technique. Now, Newton-Raphson linearizes the nonlinear system of equations into a set of linear equations, which can be solved using the matrix multiplication of the matrix inverse times the right-hand side column matrix. So we can do that. You do have to be able to take derivatives. You've got to remember some things like you are calculating delta x, and the right-hand sides to be negative of the function evaluated at the most recent points. So that one I really highly recommend because it's the most practical. But go ahead and get that set up, and then you could go through and just update functions would be my recommendation, because there are a lot of little places where you can make mistakes. Now, you will need to be able to derive what those equations are. That means taking the derivatives. Anyway, you need to be able to describe why one of these would be better than the other, okay? Like I say, Newton-Raphson will converge if you are close enough to the correct answer, okay? That linearization is the critical part. If the function is highly nonlinear, you need to be very close to the correct answer. Gauss-Seidel, simple-minded, a lot easier, but it doesn't converge quite so often. From the last week's lab, you need to be able to do curve fitting. And the number one thing you will need to, I promise you, you will need to develop a regression formula using the least squares technique. I will make you write that out on a piece of paper and upload it. So just be prepared to do that. You also then, of course, will need to actually do the curve fitting, and we have several different Excel tools that can help us with this. I do recommend doing this in Excel, not in VBA, but anyway, Trendline is really good for getting a first rough guess, but if you need to use those numbers for something, that's kind of a pain in the neck. But I use that to figure out what I think is my best target model, okay? If I need something and it is linear or only has 2 terms that I can write as something that's a linear model, maybe instead of looking at y versus x, I look at y versus x squared to get something that was ax squared plus b, something like that. To get the slope and the intercept, I can use the slope function or the intercept function to find the r squared. RSQ will get me that. And you just highlight the data. LinEst is another great tool that will tell me what all my coefficients are. If I have something that is a polynomial form or a logarithmic polynomial form, I can use LogEst. And then finally, we have the regression tool. When you need a full set of data, the regression tool is the one you want. But I usually exhaust some of those other things first before I move to the regression tool because it gives so much information. But you need to be able to look at that information it's giving you and recognize which of the stuff is not useful at the moment and which part is it that I really want to look at. Where am I going to find the coefficients I was trying to evaluate? Okay. And the last is what we're going to be looking at today. So this is interpolation. When you have a data table, sometimes we want to use linear interpolation, but we also can use quadratic Lagrange or Lagrange polynomials. Sorry, there's a different thing, Lagrange multipliers. Lagrange polynomials can be done. We're going to look at that. I'm not really going to have you do that. If you take, I have a 1-credit course doing most of these skills, but with MATLAB, and I do it a little bit more in depth there. And then using your curve fit to actually do the approximation. So those are the 3 techniques that we're looking at today. So I have a set of data here. This is kinetic data from Alka-Seltzer and water, but I have converted it over to finding the rate. Now, I did find the rate using just the derivatives, okay? The rate of change of the mass with time. And because there's a lot of noise to the data, when you turn it into a rate, it's incredibly noisy, okay? It's all over the place, quite a mess. Now, I could have smoothed this by doing a higher order derivative, right? We know how to do that. But I just did the most simple-minded delta y over delta x, or actually delta mass over delta time, to get my rates. And so now we have this really, really horrible data set. And we want to evaluate this for a rate of x equal 5 times 10 to the minus 4th, so right in here, okay? Or when it's 1 times 10 to the minus 3, so right in here, okay? So those are my 2 targets. I want to be able to estimate what the answer should be. And so I have a couple of different curve fits that I've modeled in here. We have our table of data. Here is the rate versus the time, or, yeah. Okay. So if you do linear interpolation, you can just look at this by doing the connect the dots to your data. And linear interpolation, what it is doing is it is going between 2 points and saying it's in between these two. But if you compare that to a smoothed curve fit, you can see that sometimes, like between these 2 points, that's going to be a terrible estimate. Between these two, it'll be pretty good, right? It depends on which the 2 points are. These two will be excellent, right? It always is going to make a difference what my 2 points are. And with noisy data, linear interpolation is almost always a disaster. Now I can do a little bit better if I do this Lagrange polynomial. Now quadratic is essentially what you get when you do the smoothed version of the connect the dots thing. But I can also do something a little bit better than that, which is going to use, the more points you use, the smoother you get. Again, we're not really going to be using that, but it does get me something a little better. Most of the time, what I'm going to find with noisy data, what I want to do is actually do a curve fit. And now this depends on which curve fit you think is best. If I did with all the data set, I get this blue one. If I used just the points kind of in the middle and said, well, at the beginning and end is where it was the noisiest, then I get this dotted line. And you can choose either one of those, but let's just say that I wanted to use this curve fit here. And so this is why it's important that I can not just use the default setting, but I would like to have those constants to as many significant figures as possible and not have to type in the whole function. And so that's where doing things like the regression tool can be useful. Okay, because then it's going to have my coefficients and I can point to cells and get my results. Yeah, so this is just explaining that I kind of modified the curve fit. Okay, so if we look at a different data set, now this is a smooth set of data. They have taken lots and lots of data from, many research groups, and they have smoothed it to get the average over all of everyone's data. So this, when you graph it, is a very smooth curve. In a case like this, linear interpolation is going to be very reasonable, okay? Because, again, look at the data, it's smooth, okay? If you wanted to do this for the heat of vaporization when the temperature is 14.89, we have 12 and we have 16 here. And so the heat of vaporization is this HFG column. That's heat of vaporization. And I would just simply use these two data points with these two temperatures, and I could do the forecast method and get that. Okay? When I'm using steam tables and so forth, I do this all the time. Okay? I can get this set up in my Excel file in a flash. And I frequently do this. So forecast is the way I do that. But then we also remember from thermo that sometimes we have to do things where we have what's called double interpolation. So in this case, I want 2.38 bar and 7.56 degrees C. Well, the pressures I have available are 2 and 3 bar and 0 and 10 degrees C. So to do double interpolation, you're interpolating in two variables, but it requires 3 steps of interpolation. So what we might do is find 7.56 when pressure is 2 bar, interpolating here. Find 7.56 using this 0 and 10 for 3 bar, interpolating off of this table. And then take those two pressures and interpolate to get 2.38 bar. So that's what I want you to do for today's lab. For the homework, I've given you a data set, and I want you to do these various techniques for that data set. And then I also want you to try doing this in Python, and I've given you a Python tutorial to work through on that. Okay, so that concludes our lesson. If you have questions, ask me in class.